So a few months ago, I made the declaration that I was going to abandon my efforts in quantum gravity and abandon all my research that I've been doing and like give up the topic and focus my attentions on other things that at the time I believed could be more useful. However, I've now decided against that opinion because I still believe that I'm right about quantum gravity and I still believe it's an important discussion to have, and I still believe that what I've come up with is an important step forward in the process of identifying the correct theory of gravity. So what I'm going to talk about in this video is Ouamuamua, this asteroid that entered the solar system a few years ago now that slowed down crucially on its approach to the sun, and this had astronomers and physicists baffled, and they were thinking that, well, some of them were thinking that it could be an alien spacecraft. It slowed down on approach, which is thought to be unusual for an asteroid, and it sped up again on its slingshot away from the sun. The speeding up, that sort of makes sense with current general relativity, current gravitational physics. We can kind of very much see why it would speed up again, because it's leaving the gravitational field. The force of gravity is getting progressively weaker, obviously, so that the less force of gravity over the object, it's likely to speed up. Hence, so that's quite understandable. But what's the slowing down all about? To find out what the slowing down is all about, we have to go back to the 17th century and the work of Didouillet and Lesage in this field called shadow or push gravity, which is a term that I would advise everybody to look up before proceeding with this video. But this idea of Didouillet's and Lesage's, this old idea, this connects very much to the ideas of ether and so on as well. This is the idea that there are particles of gravitational fields, that gravitational fields have a sort of not quintessence, that's the wrong term to use, a quantum, really, a smallest indivisible unit of a gravitational field. And this is obviously when we talk about quantum gravity, we're talking about what the smallest indivisible unit of a gravitational field is. So this connects very much to the idea that I've been having, that a gravitational field is really just a cloud of electrons surrounding an object made of atoms. So if you've got, for instance, a star and an asteroid, the asteroid approaching the star, the asteroid is surrounded with electrons as well, obviously, because it has its own gravitational field formed of electrons. The star obviously is surrounded by a huge cloud of electrons as well, obviously, and electrons, being both negatively charged, repel one another. So what you get is electrical resistance there between the cloud of electrons surrounding Ouamuamua and the cloud of electrons surrounding the sun. Both clouds of electrons mutually repel, and this would cause Ouamuamua to slow down, obviously. So I'm 99% certain that is the real reason why Ouamuamua slowed down on approach, is because it's this shadow or push gravity effect occurring. It's this very mysterious, very etheric, very ethereal sort of cloud or shroud of electrons surrounding objects. This just causes repulsion between the two gravitational fields, and hence causes something to slow down. So my model is very easy to test for. We can just load up an object in space, some sort of projectile, we can fire it into a gravitational field, and general relativity won't predict this. It won't predict that an object will slow down on the approach through a gravitational field. It would say that it should speed up, if anything, because it's falling down this gravity well closer to an object. It will end up speeding up, obviously around an object as well as it gets closer to it, because it will slingshot around an object and then speed up when it leaves the gravity field. But that's sort of part of the subtleties of the mechanics of how gravity works. But yeah, I mean, this is integral also to an understanding of dark matter. What we need to understand is why stars at the extremities of galaxies rotate around the galactic centre at a faster rate than stars closer to the centre. Because if you think there's all this resistance there from the huge number of particles in the gravitational fields of supermassive black holes, for instance, very close to at the centres of galaxies, These have huge clouds of electrons surrounding them, creating resistance. It's very much like molasses. It's harder and harder as you get closer to the centre to move quickly around the centre of a galaxy. When you're further out towards the edges, there's fewer electrons there, less sources of resistance, less sources of gravitational resistance between particles, and objects are freer to float faster around the galactic centre. And that's roughly speaking what would explain the observations of Fritz Zwicky and Vera Rubin and so on, and the scientists who framed the problem of dark matter in the first place, following Einstein's work on gravity in the 1910s. Getting my history of science muddled up. Oh well. So this is aptly named shadow or push gravity, because gravity is a pushing force as well as a pulling force. So it doesn't just pull objects towards it. If it did just pull objects towards, other objects towards other objects, the universe probably would never have expanded in the first place. What it needs to expand, crucially, this is dark energy as well. This is where dark energy comes into everything. What the universe needs to expand is lots of radiation building up between electron densities, which are these clouds of electrons I'm talking about. Between these clouds of electrons surrounding galaxy clusters, all these photons jiggling around between them, building up there in these recesses between galaxy clusters, and this is driving the expansion of the cosmos. Because this radiation's got nowhere else to go, it keeps getting reflected by the electrons, because as we know via quantum electrodynamics, electrons reflect light very readily. So that's roughly speaking why we have an accelerating expansion of the universe. That's why the universe is expanding at all. That's why it started expanding in the first place, other than just, nothing happening, which is what general relativity really ought to predict, that the universe would never have expanded out of a singularity, because there would be no resisting force there to trap photons, if you see what I mean. There would have been nothing there to cause the photons to bounce around in these massive recesses between galaxy clusters for 13.8 billion years, leading to the expansion of the cosmos. So that's roughly speaking what I wanted to talk about today, and I will leave you on that note, I think, just to let you mull that over and see what you think about it. Love to hear your comments. Yes, I would love to hear your comments, I would, in the below, and I'll see you soon. Thank you.